Welcome to educator.com. We're going to be talking about introducing the concept of sampling distributions. So here's the roadmap. We've been talking about probability distributions, and that's what we call probability distributions of probabilities from discrete outcomes. But now we're going on to sampling distributions, and that's what we call distributions of outcomes that are continuous. For now, we could apply the same fundamental logic from probability distributions directly to sampling distributions. We could treat them roughly similarly. But I do want to connect sampling and research methods, two topics we've covered before, with sampling distributions. And then we're going to finally talk about actually generating sampling distributions. Okay, so first let's talk about the difference between probability and sampling distributions. So in probability distributions, we're always looking at discrete outcomes, finite or countable numbers of outcomes. So for example, in binomial distributions, if you have 10 trials, you have 0 to 10 different outcomes as possibilities, right? So that's 11, right? They're discrete, they're finite, they're countable, no problem. And those in probability distributions, what we're looking for is the probabilities of those discrete outcomes, right? So we get a list of all these probabilities. And we could actually make a list because it's a finite number. Okay, now that we know that, now let's talk about sampling distributions. Sampling distributions are roughly the same idea. You have this sample space, and you want to know how likely each outcome is, the probability of each outcome, and the set of all those probabilities, that's called a sampling distribution. But here's the big difference. Instead of discrete outcomes, now we're talking about continuous outcomes. Right? So before we asked, what's the probability that 2 out of 4 random people that you pick from the United States will have a bachelor's degree. Now we might say if you pick 2 out of 4, if you picked 4 college students at random, we're not looking for the 2 anymore. That's discrete, right? We're looking for things like what is their average GPA. Right? There's an infinite number of average GPAs that you could potentially have, right? So in that way, it's not finite anymore, but it's infinite number of outcomes, and uncountable number of outcomes. Now, that is problematic for us because here we had like a list of all the different probabilities. Can you list all these outcomes? No, that's impossible. They're infinite, right? So it's by definition not listable, not put in a table-able, right? And so that's an issue with sampling distributions. But sampling distributions get their power from other sources. So we don't have to worry as much about that. But I do want you to know that this is the big difference between probability distributions and sampling distributions. But still, we're going to be trying to find things like, how do we find the expected value of these distributions? How do we find the probability of some outcome, All right. But the same overall logic is going to apply for now. And so I want to just go over the logic of the original probability distributions. All right, so basically we use probability to find, so this is, let's say, a known population, right? So we had known populations like things like fair coins, the roll of 2 fair die, I don't know, whatever, something like that. And from that, we generate a probability distribution. So a whole bunch of different values for this random variable x, right? And then the probabilities of those x's. Okay. Once we have that, then we have this sample from here. Sample, and it's actually from an unknown population. So we get the sample and we're like, is it good? You know, is it from this kind of population? Is it from that kind of population? We don't know, right? What we do is we take the sample and we compare it to the probability distribution. And we look at, is this sample very likely? Is it very unlikely, right? And from that, we judge whether this known and unknown population is similar to each other or not, right? Is it likely, unlikely, right? So that's roughly that idea. Now, we went over a couple of specific examples. One of the ones that we went over in great detail was the one with 2 die, where the random variable is the sum of the 2 die, right? So that's an example. The logic of sampling distribution is roughly similar. So we have some known population. We generate a sampling distribution this time instead of a probability distribution. And we'll talk about how to generate those later. We get samples from unknown populations and we compare it and we say, oh, is it likely? Is it unlikely? So same underlying logic. The differences are going to be in this step. How we generate is going to be different, right? And how we judge whether it's likely or unlikely, this step is also going to be a little bit different in terms of the nitty-gritty, like how we actually do it. But the concept is the same. We have this known stuff, we have this unknown stuff. We compare the unknown stuff to the known stuff. Ta-da! Okay, but let's go over that example that we knew really well. So the known let me use black here. So the known population here was 2 fair die, right? 2 fair die that we rolled, right? And we generated this probability distribution. So here we have the probability distribution. And this is a probability distribution where x, the random variable, is the sum of 2 die, right? And we also generated all these probabilities for each sum, right? So we have the sum of the 2 die, we have all the probabilities for each of those sums, right? And each of these sums is discrete and countable. There's 10, 11 of them, right? Ta-da! All right. Now, what we would do is, let's say we rolled 2 die, and we don't know if they're fair die or not. We don't know. Some shady guy gave it to us, right? We want to know, is this a fair die or not? Well, if we got a roll such as 1-1, right? If that's what our sample was, then we could say, okay, what is the probability that x equals 2? Well, that's a pretty small probability. It looks like 0.025 or something, right? So because it's a small probability, we'll say this is unlikely. This is an unlikely sample, right? But let's say we got a sample that was something like 3, 4, right? And so we might compare that to this probability where x, so to this probability where x equals 7, right? And that is pretty likely. There's like, say, 16% chance, right? And so we would say, oh, this is likely, right? So this sample, we would probably say, oh, if we got this, we would say, oh, it's pretty likely that it came from fair die. If we got this sample, we might say, oh, it's less likely, right? It's not that we stop here and say, oh, these die are unfair, because there is still a chance that you could get this, but it's just less likely, and this is just more likely. So we're judging them relative to each other. All right. Now, we're going to do something similar, but some of these steps will differ, namely this one and this one. Okay. So how do we get a sample sampling distribution, right? We know how to get probability distributions. Probability distributions are really straightforward because we use those fundamental rules of probability. Sampling distributions are different. We can't use those probability rules necessarily. So before, what we did in probability distributions was we used things like the law of large numbers, and we could sample many, many times. This is a case where we do not use probability axioms, the rules of probability. We don't use those regularities, right? We just use the law of large numbers. We pretend to sample many, 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 many times, and then we generate the probability distribution that way. We could do that. So you could flip a coin hundreds and hundreds of times, or you could use the probability principles to come up with a probability distribution. This one will take a lot longer than this one, but you know, you have to know more stuff in order to implement this. But these are also shortcuts, right? So that's nice. Well, in sampling distributions, you also have two different methods where you could come up with sampling distributions. One of these actually applies here, and that is this one. We could use law of large numbers and sample many times. Oops. Okay, so that's one way we could do it, right? Unfortunately, we can't use this one. There's no way we could use this one. But we can use something that we're going to learn about later called the central limit theorem. But for today, we are going to focus in on this one, using the law of large numbers to sample many, many times. All right. So before we go on to actually nitty-gritty generating these sampling distributions, here's how sampling distributions connects with the concepts of sampling, right? Remember, unbiased sampling, and research methods. Remember, experimental methodology versus those other methodologies? All right, so the promise before was this. If you use random sampling, right? And by random sampling, I mean unbiased, right? And if you use experimental design, we promised that you could draw sound conclusions about causation, right? We promised that that was the case. Now, in order to do this mathematically, right, in order to, because this has all been like ideas so far, right? In order to do this mathematically, the sampling distribution is sort of the engine that allows this promise to come true. Because here's what the sampling distribution does. Imagine repeating your unbiased sampling and great experimental methodology over and over and over again, like millions of times, right? What kind of distribution would you see, right? So let's say you have this great experiment that you really want to do to see if, you know, X changes Y, right? What would happen if we did that experiment over and over and over again? Over time, you would see the truth, right? You would see what might really emerge from that experiment. And that's how sampling distributions is going to help us reap the fruits of this promise. So without sampling distributions, this promise cannot fully come true. All right. So now we're going to talk about actually simulating, generating a sampling distribution. So this is the idea of how do we go from that known population and generate, right, create a sampling distribution. Well, one way you could do it is you could use what's called simulation. You could use computer programs, typically, to literally take samples, random samples, over and over and over again, and create a sampling distribution. So an example of a data set that you might do this with is something like this. So here we have an experimental design. We want to know if hamsters who get normal amount of sleep versus less sleep, which will experience more stress, right? And maybe we have a hypothesis that having less sleep leads to greater stress, right? So we're going to look at the independent variable of sleep, right? Either regular or less sleep. We wake them up, wake the little hamsters up. And then the dependent variable that we might look at is their stress hormone levels, right? So let's say we tested these hamsters. So 3, 6, 9, 10. So here's 10 hamsters in our lab, right? And 7 of them were in the regular sleep group, and 3 of them were randomly chosen for the less sleep group. And this is their resulting levels of stress hormone. What we want to know is, are these less sleep hamsters, are these insomniac hamsters, are they more stressed than you would expect by random chance, right? That's what we expect. And so the known population that we could think about is something like, these are randomly selected stress hormones. Randomly selected hamsters, right? That these 3, it's not that they're more stressed, it's just that by chance you might get these numbers to be in there anyway, right? And so we might randomly select through a computer program 3 of these numbers, 3 of the entire set of hamsters. So randomly select them and generate a sampling distribution. And maybe one thing we might want to do is get their means, right, of 3 hamsters at a time, right? So pick 3 random hamsters, get their mean, put it in my sampling distribution. Get 3 random hamsters, get the mean, put it in my sampling distribution. Over and over again, right? Until we get a whole bunch of means. Like, here's like a dot plot of a whole bunch of means, right? And the means might range from 25 all the way to 64, right? So the mean can't be it can't be equal to or greater than 64. It can't be less than or equal to 25, right? It has to be somewhere in between. All right, and then we want to know, okay, now we have these less sleep hamsters. Sleep-deprived hamsters, that makes more sense. So sleep-deprived hamsters, right? And so maybe we'll calculate their mean. And so we could calculate their mean. So that's 55 plus 55 plus 64 over 3. So 58 is their level of stress hormone. So here we have X bar is 58. And we want to know, is this likely or unlikely given this sampling distribution? Right? So we want to ask likely or unlikely, right? If it's likely, then we might say, oh no, it's just, we can't separate whether this is due to less sleep or it's due to chance, right? But if it's very unlikely, we might say, oh, we don't think it's randomly selected. It's not that you randomly selected these hamsters. It's unlikely that you randomly selected these hamsters. It's more likely that something special's been done to them. And we know what that special thing is. It's that they've been deprived of sleep. And in that way, you can make some conclusions, right? Now, you can't necessarily say for certain whether sleep causes hormone levels to rise. It's not that you looked at the mechanism and saw the sleep causing the hormones to rise. It's not necessarily that. But you can say whether this is a likely sample given random processes, or you could say it's unlikely given random processes. And that's really all we can know from this kind of logic, right? But that kind of logic will still take us far. All right. So here we go. Here are all our hamsters, and here's our known sample of less sleep hamsters. So it's this guy, and, or I don't know if that's that guy. Maybe it's that guy. Who knows, right? So it's those guys, right? But, maybe it's just that they were randomly picked. Who knows, right? In order to generate this sampling distribution of the mean, right? Here's what we did. First, I'm really just summarizing in steps what we talked about before. So first what we did was take random sample of 3 hamsters. And here we'll call that n, right? Because n is the size of the sample. Then what we did was we computed a summary statistic. We computed the mean, right? But, we could have computed standard deviation. We could have computed, median, right? So some summary statistic, right? And then number 3 is the important step. Repeat steps 1 and 2, right? So you do this over and over again, and that's what it means to simulate a sampling distribution. And the 4, examine and plot resulting sample statistics. So here, these are all means, right? So that's a mean, that's a mean, that's a mean, right? It's a mean of 3 that have been selected, right? And so if we repeat this, if we repeat these 2 over and over again, and then we plot it, then we'll see the distribution of samples, of sample statistics, right? And that's why it's called a sampling distribution. Ta-da, right? And so once we have a sampling distribution, then you could see, oh, it has a expected value. We could find the mean of this thing, right? It's like a meta mean. It's the mean of means, right? And we could find the standard deviation of this thing, right? And so that's what we mean by expected values. Okay. Okay, so now let's compare these 2 things. So we know the logic of probability distributions. Now let's apply that same logic to sampling distributions. All right, so here we go, known population, 2 fair die, probability distribution, it's the same thing, I just made it sort of small. Here's a likely sample, here's an unlikely sample, right? And we know it's likely by looking at this probability distribution. We know this is unlikely by looking it up in this probability distribution. Okay, so pretty straightforward. What about in terms of this hamster stuff? So the known population is all the hamsters in our study. Not only that, but our mechanism is just like here we think it's 2 fair die. Here we think it's all hamsters, and they were 3 chosen randomly, right? We could simulate that process, right? We could choose 3 randomly and find a sampling distribution. And these are all means now, right? Not only that, but we could find a likely sample, which might be something like, 47, So if we found that we found a mean of 3 hamsters, so our sleep-deprived hamsters were had a mean of 47 in their stress hormone levels, we might say, well, it seems very similar to chance, right? So it seems like they're not that different from just picking hamsters at random, right? But we might have an unlikely sample. And here we had, in the example I showed you, we had 58. And 58 is over here. And that might show us, that's really unlikely that we would choose 3 hamsters at random and get such a high mean, right? And so in that sense, we could start thinking, oh, okay, this is likely to have come from random generation. This is less likely to have come from random generation.